Yeah, this is uh, Introduction to Machine Learning, Week 7. Uh, my name is Rohan, and I am a TF for this course. I'm a PhD scholar at IISc Bangalore. So, this week we'll cover mainly, I mean, two overall topics. One would be computational learning, and another is ensemble learning. So I saw the assignments for this week. They barely gave any questions from computational learning from the first part. Uh, the questions were mostly on ensemble learning, on bagging and boosting, and those parts. But we'll cover the computational learning part as well, and I will highlight the areas from where you can, I mean, questions can be asked in the final exam. This assignment, there were very few questions, but in the final exam, there might be questions, and I will highlight those parts. Uh, you know, I will try to give you some sample questions that could be asked. Right? And we'll also solve some few examples on ensemble learning on random forest and Adaboost as well. Okay. So, okay. So let's begin with first with uh, uh, computational learning theory. Okay. So I think you guys are all familiar with what are instances, what are instance space, right? So instances are each of the uh, examples or each of the um, you know data data set that you have, right? Those, that is your whole instance space. Now, what is concept? So if you look at this diagram, so this concept C. So this is basically your actual representation of your data set. So this concept clearly separates which is your positive data or which is your negative data, right? And hypothesis. So what is hypothesis? Hypothesis is uh, is the model's presumption between the connection between the input features and the result, right? So I'll explain this with an example, uh, and then I will explain what are PAC models, right? So before that, let me come to my whiteboard. Okay, right. So right. Okay. So let's start with the what is hypothesis, right? So you can think of it in many ways. So one way to think of it is a hypothesis is a function that best uh, represents uh, the target variable. So what do I mean? For example, we have done uh, we have done linear regression, right? So in linear regression, let's say you have this. Let's go back to our standard example of, you know, housing prices with respect to area of the house. Let's say. So you have some data points in your uh, some data points that you have collected. Now to fit these data points, you draw a line in case of linear regression, and this line is, let's say, a straight line, which has the equation of y equals to mx plus b. So then this y equals to mx plus b, that becomes your hypothesis, right? So you are choosing this function to represent your target variable. In this case, your target variable is the housing price, right? Whereas concept is basically your actual data that you have. For example, the black points that I have drawn here, right? So the actual data. Now, obviously, you would want uh, to have a hypothesis which best represents your actual data, you know, uh, which is not very much different from your actual data, right? So, because you want to predict your housing price as accurately as possible, right? So, you want the best hypothesis. Now, let's think of another example. So, let's say you have some variable x and your target variable is y. You have your independent variable is x, target variable is y. So x, if x takes 0 value, y takes 1 value. If x takes 1, y is 0, right? And you have this data um, in your data set. Okay. Now, what could be one possible hypothesis that uh, you can have in this case? Okay. So what we are doing here is we are targeting Boolean functions or Boolean variables. So x is a Boolean variable which can take only 0 or 1 value, and yeah, y similarly, the target variable is also Boolean. So in this case, what will happen is that the possible number of values that x can take is 2, right? Okay. Now, uh, corresponding to these two values, so these two values are 0 and 1, right? X can take 0 and 1. Now, corresponding to these two values, the possible number of hypotheses that you could have, right? For example, you could have one case where x equals to 0, y equals to 0, x equals to 1, y equals to 0, x equals to 0, y equals to 1, x equals to 1, y equals to 1. So these are the all possible hypotheses that you can have, right, in your case. Now, if x has two hypotheses, x can take two values, then number of possible hypotheses is 2 to the power of 2, right? Because y can also take two values. Okay. Similarly, let's say that if x can take three values, which is 0, 1, 2, whereas y can take only, let's say, 0 and 1, only two values, then how many possible number of hypotheses that you can have in this case? That is 2 to the power of 3, right? This is your hypothesis space, capital H. This is the number of elements in your hypothesis space, right? So you can think of it like, if x takes zero value, y can take zero value. If x takes zero value, y can take one value. Okay, and like that, right? Sorry, actually it will be 3 to the power of 2, not 2 to the 2, 2 to the 3. Okay, yeah. So yeah. So actually, for you can visualize it in this way. So for every value of x, so if x takes zero value, right, then y can take two values, right? Similarly, okay, no, actually it is 2 to the power of 3 only. Right? Okay, okay, let's derive it. So for example, let's say that if x takes zero value, y can take two values, okay, 0 or 1 corresponding to zero value. If x takes 1, then y can take again two values for 1, that is into 2. And again, if x takes 2, then y can take again 2 values for that. So that is 2 into 2 into 2, 2 cube, right? So total hypothesis space has 2 to the power 3 elements, right? So this is similar to the multiplication rule that we actually described in when we are doing probability uh, in week 4, I think. Okay. Okay. So similarly, uh, okay. Now coming back to this example that we had. Okay, this example. So here, what we are doing. So this is our data that we have. Now, can we represent a function which can you know, which can uh, resemble this data, right? So if you have like attended the last lecture, you could have known that we are discussing logic gates. So this is exactly the not gate, right? So y equals to not of x, right? So it's just if x is 0, then y is 1, x is 1, y is 0. So that's just the not gate, right? For example, you can also represent it like this. This is the symbol for NOT gate. If you input X, it will give you output as Y, right? Now, let's look at if instead of one input variable X, let's take two input variables X1 and X2. And your output variable is Y. Now, in this case, how many possible hypotheses that we can have? So let's count it out together. So x1 x2 can take values like 0 0 0 1 1 0 1 1, right? So there are four sets of values, and y can take two values for each of these four sets of values, right? So the total number of hypotheses is 2 to the power of 4, right? Now to generalize it, so let's say you have x1 till xn, you have n input features, n input boolean features, right? So for those boolean features, how many values, how many different values that these set of boolean features can take? So for example, x1 can take two values. Similarly, x2 for each of those two values of x1, x2 can take two values till n times. You have to multiply n times, that is 2 to the power of n. So in this case, in the example that we are showing here, x1 and x2, like there are two variables, so they are taking 2 to the power 2, that is four values. So this is actually 2 to the power 2 that we are doing. But in the general case, if we have 2 to the power of n values that the input variables can take, corresponding to this 2 to the power of n values, y can take, that is our hypothesis space will become 2 to the power of 2 to the power of n, right? So this is our hypothesis case if we have n input variables. Is it clear till now, or uh, is there any question? Okay. So now, as I said, there could be, your hypothesis space could be this big, 2 to the power of 2 to the power of n, right? Now, let's take one example. Let's take one specific hypothesis case. So, for example, let's say in this example, when x1 is 0, x2 is 0, y is 0, this is 0, 0, and 1. So, this is one example that you can say. Okay. Now, what is the best hypothesis that represents this function, right? I mean, again, if you have attended the previous lecture, you would know that this is a AND gate, right? So y equals to x1 and x2, right? This is the best hypothesis that represents this data. Okay. Also, you can diagrammatically represent it as like this: x1, x2, and here you get output as y. Similarly, if you have like n you know input features x1 till xn, you can find out what uh, what combination of and or NAND nor all those gates, and finally you can find out what could be your best hypothesis. Okay. Now, one question that could be asked in an exam is uh, okay. Let me is the concept of uh, what is a consistent hypothesis and what is a inconsistent hypothesis, right? So questions could be asked like, okay, they have given you some data set, and in the options they will ask you that okay, out of these four options, tell me which is a consistent hypothesis. Now before that we have to know like what is a consistent hypothesis and what is an inconsistent hypothesis, and I will explain it with an example. So let's say you have some data, and your data set contains these features of different persons, and the features are the first one is BP, that is blood pressure, obesity, and the third one is exercise, and the target feature is uh, let's say heart disease. Okay. Now let's say your first example is uh, let's take that this first person has high BP, H for high, has obesity, yes, exercise, no. So that person doesn't do exercise, and that person, let's say, has heart disease. Okay, why? Next person again has high BP, has obesity, does exercise, but he doesn't have heart disease. Okay. Third person has high BP, obesity, doesn't do exercise, and has heart disease. Okay. Now, uh, now you have been given two hypotheses. Okay. So let's take one hypothesis as this one. So has high BP, has obesity, and next one is left empty. And another hypothesis is uh, the first two are left empty and the uh, exercise is given as no. So what does this hypothesis mean? Okay. So you have been given two hypotheses. Let's look at the first hypothesis. Let's look at one by one. Okay. So what does this actually mean? So this one. So this one means that I can predict whether that person has heart disease or not using this hypothesis. And this hypothesis means that if the person has high BP and the person has obesity, doesn't matter he does exercise or not. But if the first two conditions are satisfied, then the person should have heart disease. And if the first two conditions are not satisfied, then the person should not have heart disease. This is what the hypothesis is telling. Okay, this is what is the meaning of the hypothesis, right? And the second hypothesis, similarly, means that doesn't matter whether the person has high BP or obesity. If the person doesn't do exercise, then he has heart disease. And if the person, uh, does exercise, if basically this condition is satisfied, if exercise equals to n, then he has heart disease. If exercise equals to y, then he doesn't have heart disease. Now, question could be given like this, that you could have multiple hypotheses and you have to choose which is a consistent hypothesis, which is an inconsistent hypothesis. Now how to do that, right? Now let's check for the first hypothesis. Okay, now let's check this hypothesis whether this is consistent or not. So we will go one example by one example. So we'll match it with the first row. Okay. So the first row, if you look at the first row, so here if you have high BP. Okay. So the first condition is matched. Okay. Second condition is it should be obese, right? So here it is given as Y. So that is also matched. So obese. Obese is matched. So this is also matched. So they are saying that if these two are matching, doesn't matter what is exercise, that person has heart disease. So it matches. So the first example matches. So it is consistent with the first example, right? Now coming to the second example. So the person has heart disease, high BP, that matches. The person has obesity, that also matches. But the person do not have heart disease. So remember what I said, that if these two conditions are satisfied, then the person should have heart disease. Only then this is a consistent hypothesis. But this n, this is not satisfied because here the heart disease is n, whereas the hypothesis is predicting it to be y. So second example is not satisfied. Okay, you can check for third example similarly, and it satisfies. But since one example is not satisfied, then that means that this is an inconsistent hypothesis, right? Similarly, now if you check for the second one, the second hypothesis, exercise is n, that means heart disease is y. So if we check with the first example, exercise n, heart disease y, that matches. Okay, that matches. Okay, second example, exercise n, which is not satisfied. So if it's not satisfied, then it should give n, which is actually true. So it is giving n. Now the second condition is also satisfied. Third condition, n, and it is y. So it is satisfied, right? So this is an example of consistent hypothesis, right? Is that clear? So we described what is hypothesis, what is a consistent hypothesis, what is an inconsistent hypothesis. Okay, let me know if there are any questions. Okay, let me go back to my slide if there are no questions. Okay. So, okay. What could be the reason for inconsistent hypothesis? So, I think we have learned it in previous lectures that due to restriction bias and preference bias. So, for example, in general, in practical life, your hypothesis space is infinite, right? So, if you saw from the Boolean example, the hypothesis space grows exponentially, 2 to the power of 2 to the power of n, right? So, if you have a lot of data, your hypothesis space is basically grows very fast, grows exponentially, and it's not possible to you know take into account all the possible hypotheses that are there. So you have to restrict yourself to consider only a certain limited class of hypotheses, right? That is what the restriction bias is all about. Now, preference bias is something that, okay, you prefer some hypothesis more than some other hypothesis. So we will see this through an example later on when we will do random forest or Adaboost algorithm. So where we will see that we will prefer shorter trees than longer trees, or if we do it vice versa, right? So that is a preference bias. Now, this is just there is some terminology that, some mathematical terminology that we'll do, but after that, we'll see how to solve problems uh, which could be asked in the final exam. Okay. Okay. So okay, now these are called PAC models. So why PAC? So PAC stands for probably approximate correct models. So since you don't have, you cannot, explore the full hypothesis space because it's a very big space. So you try to make an approximate model of your data, right? It's not an exact model, and that's why it's a probably approximate correct. And you make this approximate model and you try to predict what could be the error of this approximate model. Now, when you are doing the error, so as I said, this is your concept space, which is the uh, you know, actual data that you have or actual hypothesis that you have, but you are making a approximate hypothesis. This is H. Okay, so these two will disagree. Now you have the error would be the probability that this concept is not agreeing with the hypothesis, right? So that is the error. So the error is basically in these parts. So this part where C is not matching with H, and this part where H is not matching with C. So this is represented by C XOR H, right? So this is your error part, right? Now, okay. So here in the second line, if you see, what is the probability that RH is basically your actual hypothesis space, that is a concept, minus the predicted hypothesis. This is the hypothesis that you are assuming, approximating, right? So hat is represented by the approximation, whereas RH is the actual, um, yeah, the actual thing, the actual concept. So the difference between these two should be less than epsilon, where epsilon is a small quantity. So you want to calculate what is the probability that my hypothesis is not matching the concept, and that mismatch should be less than some small value. You want epsilon to be very small, because you want your mismatch to be very small, and the probability with which this value is less than epsilon should be greater than 1 minus delta. So again, delta is a small value, so this probability should be very high. We want this probability to be very high, actually close to 1, as close as possible to 1. Okay, so in when questions will be asked, they will provide these values like epsilon and delta. They will provide you these values, right? I will tell you what possible questions they can ask, but these values will be provided. Okay, so this is on your hand, right? So for example, you would want epsilon to be the mismatch to be very low, let's say 5%. Then you choose epsilon to be 0.05, and the probability with which you can uh, you know want your model to be accurate, the probability could be, let's say you want 95% accuracy. So in that case, you can set your delta to be again 0.05, so that 1 minus 0.05 is 0.95. Or if you want 99%, then you can set delta as 0.01, and then you will have higher probability of getting the within the error bounds. Now, how to calculate this error in the training set? So this is the actual error, okay, and this is the in the training set. So if you remember from the confusion matrix, okay, so we have this true positives, true negatives, then you have false positives and false negatives. So false positives are those which are uh, actually negatives but are tagged as positive, and false negatives are those which are actually positive but are tagged as negative, right? So this is where, so basically you see the false positives and false negatives are the ones which are not actually matching with your exact observations, right? So that is where this Cx is not equals to this hypothesis x. So hypothesis x is the one which you are predicting, and Cx is the actual observed one. So you basically take the total number of false positives and total number of false negatives, sum them up. That is where this summation happens. That is what this numerator is talking about. So I'm explaining this in very simple terms, right? So this is all very mathematical, but simply looking, all these stuffs, okay? Because this is just the false positives plus the false negatives, which are basically the error divided by the total number of training examples. This total D, right? Okay. So I think we have done this multiple times, and you can easily calculate this thing. So I think, for example, they could give some data set, and they could give the actual prediction, actual value of the target variable and the predicted value of the target variable, and they can ask you to calculate what is the error, right? So you can do that easily, right? Okay. Now, okay. So there are some bounds that we are going to define for this finite hypothesis space. Okay. So if the space is, so all these are applicable only for finite hypothesis space. Okay. So as we saw earlier that the hypothesis space is for a Boolean set of n input variables, the hypothesis space is 2 to the power of 2 to the power of n, right? So like that. Okay. So now let me do a derivation of this. So on one side, we'll consider that my hypothesis is consistent. Okay. Now, what is this inequality saying? This inequality is saying that if my hypothesis is consistent and my total hypothesis space is H, this is the size of the total hypothesis space, and these are the epsilon and the delta that we have earlier talked about, this will pretty much be given. Then you might be asked to calculate how many number of examples that we need to have so as to satisfy this condition, this this condition. Basically, my probability of mismatch less than equals to epsilon should be greater than equals to 1 minus delta. So uh, you're basically making a bound for your error. Your error bound is epsilon, and what is the probability of that error bound is greater than 1 minus delta. So to satisfy that condition, what is the minimum number of examples that you need to have, right? So you can intuitively think that, okay, more the number of examples that we have, you can better train your model and you can minimize the error, right? So in order to have a minimum error epsilon, what is the minimum number of, sorry, in order to have a maximum error epsilon, what is the minimum number of examples that you need to have? That is given by this equation. Similarly, if you reverse it, the error, so this gives a upper bound for error. So they could also give you that, okay, my data set has m number of samples and my hypothesis space is, let's say, 2 to the 2 to the n. In a Boolean case, they could also give some other hypothesis space. They could give some delta, and then they might ask you to calculate what is the uh, you know maximum error that we can have for this data set, right? So this is just reverse of this formula. So if you just take epsilon on this side and m on this side, the inequality will be reversed, and you will just have this. Okay. So you just have to memorize this formula, and you can solve for the number of training examples. So I'll just quickly derive this formula. So this is for a consistent hypothesis. The right side is for an inconsistent hypothesis, which I'll come to after I derive this for the consistent part, consistent hypothesis case. Okay. So let me go back to my whiteboard. Okay. 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 So what we are doing here is let me, okay, bounds for finite hypothesis. Okay. Now we are looking at consistent hypothesis. Okay. Now let's go back to our initial definition. So what was the initial definition? So the initial definition was that uh, probability that my hypothesis and concept are mismatching uh, is less than epsilon is equals to 1 minus delta, right? Okay, actually greater than equals to, but yeah, okay, greater than equals to 1 minus delta. Now, if you have attended the probability lecture, you could see that, okay, now if I have uh, probability that this error is greater than, less than epsilon, what will be the probability that my mismatch is greater than epsilon? It's just complement of that. So it is just 1 minus this thing, right? Probability of h minus c is less than epsilon, and this probability is delta. 1 minus delta, 1 minus 1 minus delta, this is delta. Okay. So also intuitively you can think that, okay, my mismatch is less than epsilon. If the probability is 1 minus delta, then what is the probability that my mismatch is greater than epsilon? It should be inverse, right? 1 minus of that thing. So let's say if you have very high probability, 95%, that your error is within within epsilon. So what is the probability that your error is, higher than epsilon? That could be basically be 5%, right? Okay. Intuitively, you can also think like that. Okay. Now, let's say you have some bad hypothesis. So let's say you have k bad hypothesis. Okay, h1 till hk, which have error greater than epsilon. So as I said, there is 5% chance that you could have some bad hypothesis which have error greater than epsilon, right? So these k comes in that 5%. Now, what is the probability that hi is consistent? So you try this, uh, examples. Okay. So sorry, you try this hypothesis. So you take any random hypothesis and you check whether this hypothesis is consistent or not. So what is the probability that this hypothesis is consistent? So it's 1 minus epsilon, right? So there is very, if epsilon is very small, if your hypothesis is very strong, you have a very high chance that your hypothesis is consistent, right? Whereas if you have a very high error, if epsilon is very high, then you have a low chance that uh, hi is consistent. Then 1 minus epsilon will be low. Otherwise, if epsilon is small, 1 minus epsilon will be high, right? So again, intuitively, you can think that error is low. That means hypothesis is good. That means probability of hi is consistent is high, okay, and vice versa. Now, this is for one example. Now, if your training set has m examples, so what is the probability that hi is consistent for m examples. So it is 1 minus epsilon whole to the power of m, right? Okay. So it is consistent for first, just the multiplication rule again that we have discussed in the probability lecture. Okay. Okay. So, okay. Now, there are k such hypotheses, as we said, that there are k bad hypotheses. So, what is the probability that uh, hi is consistent for m training examples and for k hypothesis? That is k times 1 minus epsilon whole to the power m, right? And this is less than the total hypothesis space. So because k, how many maximum number of bad hypotheses you can have? That is the total number of hypothesis space, right? So that is h into 1 minus epsilon whole to the power of n. That is the total. That is the probability that it is consistent. Okay. Now, sorry, total probability that hi is consistent and has error greater than epsilon. So if you remember the first condition that we said that these bad hypothesis has error greater than epsilon, right? So here if you see, so error greater than epsilon. So what is the probability that error is greater than epsilon? That is delta, right? So here we have calculated delta, right? So this should be less than delta. Okay, this is the condition that we have obtained. Now from this inequality, we have to find the value of m, right? Okay. Is there any question till now? Okay. If not, then we'll just solve this inequality. Okay, the inequality is 1 minus epsilon whole to the power of m less than equals to delta. Right? Now, there is another inequality that we are going to use here. The inequality is given by 1 minus x is less than equals to e to the power of minus x. Okay, I'll just explain in a minute, like how where did this inequality comes from. So, like e to the power of x has a Taylor expansion, Taylor series expansion like this. So those who don't know Taylor, what is Taylor series expansion, no need to worry. It's just a simple thing. You can just look it up, or if you have any questions, I can explain it uh, now in few steps. But without going into that, we have basically Taylor series expansion of every function. Let's say sine, cos, tan, log, everything. Similarly, e to the power of minus x is a Taylor series expansion of this thing. Now, what we are saying is that, okay, we are considering terms only up to this, up to 1 minus x, and we are neglecting the higher terms, right? So, if you see there is a plus term, plus of x square by 2, so that means e to the power of minus x is actually greater than 1 minus x, okay? Because you have some terms, some positive terms added to this this part, okay? So you can easily see that, okay, e to the power of minus x is greater than 1 minus x, okay? Now we just apply this over here, that 1 minus epsilon, we just replace it with, uh, so h of 1 minus epsilon whole to the power of n is less than equals to h e to the power of minus epsilon m. Okay, I just replace 1 minus epsilon with e to the power of minus epsilon. Okay, and that is less than equals to delta. Okay, now what you do is you take log on both sides. So this is the inequality that you have, and you take log on both sides. So if you take log base e, okay, so log of h. So if you are not familiar with the properties of log, so I'll just write down a few properties, and you let me know if you are not aware of this. So log of ab is log of okay, wait a minute. Okay, log of ab, it's not visible. Let me see. Log of AB equals to log A plus log B. Okay, again here all the bases are E. Actually, this formula is valid for any base. Okay, so it doesn't need to have E base. Okay, but here when we're doing log, here we will take base E. That is one thing. And again, log of E to the power of here base E. So when I write ln, that means it's with base E, log base E. So log of E to the power of A equals to A, right? So we'll apply these two properties of log, right? So here you can see log of AB. If you apply it over here, so log h times. Uh, so if you take h as A and e to the power of minus that thing as B, so we have log of A plus log of e to the power of minus epsilon m less than equals to log of delta, right? And again, if you apply the in the second term, if you apply the second transformation, the first formula log of e to the power of a equals to a, so we'll get minus epsilon m, right? So what will happen? So log of h minus epsilon m is less than equals to log of delta. And similarly, if you just change side, epsilon m is greater than equals to okay, minus epsilon m log of h. Okay, what they're doing is that uh, let me see. Okay, since it is minus em you have, so you multiply both sides with minus. So here you will get plus minus minus, right? So epsilon m and is greater than equals to log of h minus log of delta, right? Okay, since we are multiplying everything by minus, the inequality will change. Okay, so this will become actually greater than equals to, since we're multiplying by minus 1. Okay, so I skipped one step, but I think that's okay. We just multiplied minus, the inequality flipped, and epsilon m is greater than equals to log h minus log delta. Now if you see that this term minus log delta, again there is just one formula, that minus log delta is basically log of 1 by delta. Okay, so log h minus log delta, I can write it as log h plus log 1 by delta, right? And from here you can say that m is greater than equals to 1 by epsilon log h plus log 1 by delta, right? So yeah, this is it. This is the derivation, but for exam purpose, you can just memorize this formula if you want this thing. So again, as I said, they will uh, provide you values of epsilon and delta. They can ask you what is the minimum number of examples that you need to have so that your hypothesis is consistent. Okay, and this uh, size of the hypothesis space and those things you can calculate. So, for example, let's say we have Boolean uh, inputs, n Boolean inputs. The hypothesis space will be 2 to the power of 2 to the power of n, and so on. Like we saw how to calculate the size of the hypothesis space. Similarly, if they give you the number of training examples and the hypothesis space and delta, they can ask you to calculate the error. Okay. Okay. So this is for a consistent hypothesis. Now, if your hypothesis is not consistent, then what will happen? Then how to calculate the minimum number of examples that you need, or the maximum error that you can have. So I'll just quickly go through. The process will be same. Just we did the derivation for the consistent. We'll not do derivation for inconsistent hypothesis because the process is exactly the same. You will get the same inequality. Here, the only difference is in the first line, right? So here, the first line is saying the probability that your true error is greater than the training error plus some epsilon, that is given by this h times e to the power of minus 2m epsilon square. Okay, right? So this is just the this is actually derived. Like how this comes h e to the power minus 2m epsilon square. This comes from some theorem in mathematics. I'll not go into detail, but this is just, you have to remember that for inconsistent hypothesis, uh, the the probability that your true error is greater than some training error plus some epsilon is given by this. And from here, again, you can do it less than equals to delta. And from there, you can take log and, solve the inequality. And finally, you will get something like this. Okay. So only difference is instead of, epsilon here, you get 2 epsilon square, right? So that is the only difference, right? And similarly, if you are to calculate the maximum true error that you have, that is the training error plus root over of this. So if you just take epsilon on this other side, the epsilon would be less than equals to root over. So here you see you have epsilon square. Here you have epsilon. So if you have to go to epsilon, you have to take a square root of this, right? So epsilon would be less than equals to square root of ln h plus ln 1 by delta by 2m, and your true error would be training error plus this thing. So you already know how to calculate training error. I just explained it in the previous slide. So number of false positive plus false negatives divided by total number of training samples. So they could give you some data. From there you can calculate the training error, and they can ask you what is the upper bound on the true error, right? So you calculate the training error, the hypothesis space is given, delta is given, number of examples is m, that is given, and you have to calculate true error. So you can do this, right? Okay. So again, this is just based on the formula, but these are the questions that could be asked. Okay, let me know if you have any questions, or we can move on to the next topic, which is VC dimension. So VC dimension. What is VC dimension? So this is these construct a hypothesis so as to separate the positive points from the negative points, right? So, and these 3 points could take any possible values. For example, in the first case, you see, uh, okay, I think YouTube is buffering. Okay, is it okay? Okay. Okay, so I was saying, yeah. So these 3 points could take any values. So, for example, this point is plus here. You see that okay, now this point is plus. This is this point was negative earlier. This point is plus. So again, there could be with these 3 points, we could construct basically. So this point can take two values, plus and minus. This point can again take two values. This point can again take two values. So we can construct eight such two cube basically, two to the power of three, two into two into two, eight such uh, hypothesis space, right? That we can construct from here. And for each of those data set, we can construct a line. So if I say that, okay, I want to, my problem statement is to, separate the positive examples from the negative examples with just a line. So if I have such eight examples, we can surely say that, okay, we can construct this line so as to separate the positive points from the negative points. We can really do it, right? But instead of, you know, 3 points, we have these 4 points. There is no way that we with a single line we can separate the positive points from the negative points for all the cases, right? So here if you see we have 4 points and there is no way that we can construct uh, a single line with which we can delineate the positive examples from the negative examples in all the cases. In some cases you might, but in all the cases with 4 points you cannot, right? So this is the concept which is called shattering of the points. So a line can shatter 3 points, but it cannot shatter 4 points, right? So the VC dimension, the formal definition, if you see here, is the size of the largest set of samples that can be shattered by H, right? So here your hypothesis space is a single line, and the largest set of samples that can be shattered by H is 3. You cannot do 4, right? So your VC dimension is 3 in this case, right? Okay. So here you can see that if you have like at least one set of size k, that H can shatter, and there is okay. In order to prove that VC of some hypothesis is k, you have to say that okay, there is at least one set of size k that H can shatter, and there is no set of k plus 1 points that can be shattered, right? Okay. So for example, here k is 3. So if I increase k to plus 1, k plus 1, that is 4, it cannot be shattered, right? So, but for all possible k equals to 3, we can shatter the space by a single line, right? So that's why in this case, the VC is 3, right? So again, for if you have in your sample space, if you have m instances, you could have 2 to the power of m levelings for Boolean values, like we have seen earlier, right? If you have x1, x2 till xn, you have 2 to the power of n possible values that your input features can take. And if h shatters s, then your h should be greater than 2 to the power of n. And in that case, your VC should be less than log of h base 2, right? Okay. So this is simply saying that for a Boolean case, your for example, if I try to relate this formula with this example, so you see here you have like 3 points, you have three instances, right? 1 2 3. So your m is 3, you have 2 to the power of 3, that is 8 levelings. So your hypothesis uh, should be uh, greater than 2 to the power of 3, that is, should be greater than equals to 8, because for each of these 8 cases, you should have 8 different lines. Right? So that's why your hypothesis is 8. And your VC dimension would be log of 8 base 2. Log of 8 base 2 is 3, right? So your VC dimension is 3 in this case. So that's what you get again, right? So this is how you calculate VC dimension. So here is another example on this right side. If you see, here your hypothesis space is uh, rectangles. So with rectangles, you need to separate the uh, positive points with the negative points, right? And these rectangles should have their axis parallel to the x and y axis. So actually, the sides parallel to the axis, right? So you can construct any set of 4 points. Like this could be positive, this could be negative, positive, positive, and so on. You could have 2 to the 4 possible uh, options, and for each of those options, you can construct some rectangle which has sides parallel to the axis, which can separate the positive points with the negative points. So in this case, let's say you have all negative points. So your rectangle could be this. In this case, you have 2 positive points, these two. You can construct a rectangle like this to separate the positive points from the negative points. Here are 3 positive points, like this, you can do it, and so on. So in this case, your VC dimension is 4. Okay? Is that okay? All right. Let me know if you have any questions. Okay, moving on to Ensemble Learning. So, what is Ensemble Learning? So, all these days we have seen different algorithms, starting from linear regression, logistic regression, decision trees, and neural networks, and so on. Now, what if we combine two algorithms, right? Or let's say in case of decision trees, what if we combine two decision trees together? Then what will happen, right? So that is the concept of ensemble learning. So if you have one model, if you have like multiple models, you basically combine those models and make a single model out of that, right? So how can you do that exactly, right? So these are the 4 ways you can do that. First is different algorithms. So as I was saying, you have learned different algorithms, decision trees, linear regression, and so on. So you combine different algorithms, or you combine different hyperparameters, right? We have also learned, for example, the depth of a tree is a hyperparameter. So you can combine, a lower depth tree to a higher depth tree, and so on. You can combine different representations. For example, while we're doing neural networks, we saw that an image could be represented as pixels. You could, lower the dimension of the image, then you get a different representation of the image, and so on. So you can also take different representations and combine them, or you can have different training sets, right? For example, you don't train your model on the whole training set at once. You can take chunks of the data and build different models and combine them, right? So this is basically the concept of ensemble learning, right? Okay. Now The question is, uh, will it reduce our error? Okay. So let's say that your individual error was of a model was something, let's say 10%. Your individual model had accuracy 90%, and therefore the error was 10%. So what will happen if I combine, uh, let's say, two of those models? So what will be the accuracy now? So your error was 10%, that is zero point 0.1. So if you combine two of those models, the error will become zero point 0.1 whole square, that is 0.01, right? So now your new model will have accuracy of 1 minus the new error, that is 0.01. So it will become 99% accurate, right? So from 90% accurate, it will become 99% accurate, right? So let me give you an example. Okay. So let's say that, as I was saying, your error for the first a single model is zero point 0.1, right? Now, if you combine two models, your error will become e square, and zero point 0.1 square is 0.01, right? Okay. So similarly, if you have two different models, so for the first model, your error is zero point 0.3. For the second model, your error is zero point 0.7. Your after you combine this model, your error will become epsilon 1, epsilon 2. It will be 0.21, right? So your accuracy would be 1 minus 0.21, right? That is 79%. Okay. So earlier this model, if you look at the individual models, okay, so individual models had 70% accuracy. This one has 30% accuracy. So you combine these two less accurate models to make a more accurate model. Now your accuracy has increased. This accuracy is more than the individual accuracy of the models, right? So this is how you uh, increase the accuracy by doing ensemble learning, right? Is this clear? Okay. Let me do this another example. Okay. Uh, so let's say you have two models again. The first model has error zero point 0.3, second model has error zero point 0.5. Okay. Now you want to calculate. Uh, so let's say you're predicting some value. Okay, and your model one. So you are using basically model one twice, and you're using the second model once. Okay, you can do that. So for example, you are you are combining uh, the first model twice and the second model once, right? And your first model gives correct value, right? whereas your second model will give incorrect value, incorrect prediction. So in that case, what we'll do, since your second model is giving incorrect prediction, so the total error would be epsilon 1 square times 1 minus epsilon 2 square. Sorry, not square, because you are using the second model only once. So 1 minus epsilon 2. So that will give you zero point 0.3 square times 0.5, right? So that is point, 0.045, 0.045, right? So that is what is given in this example actually. So you have three classifiers. So R is the probability of mistake of for individual classifiers, right? And so your probability of error would be 3r squared times 1 minus r plus r cube. So this r cube is when all the classifiers are giving correct prediction, and this is for when two classifiers are giving correct prediction and one classifier is giving incorrect prediction, right? So for incorrect prediction, my error would be 1 minus epsilon, right? Okay. So there is a question. Prerna is asking, Ensemble learning is redundant type, then the error should be increased. No, so ensemble learning is not redundant. So you're combining two weak models to make a stronger model. It is not the same model twice. So, for example, okay, so when I said same model, I meant that in the case like, okay, let me give you an example first. So let's say you have two decision trees. So I meant same, when I meant same model, I meant both are decision trees. Okay, that doesn't mean that both has to, you know, both has to have the same cut. So, for example, you are making a decision tree with some feature in one case, and you are combining it with a decision tree with a different feature and a different cut, right? So it is not redundant. It's not the same exact same thing twice. We are doing some variation in between, like we'll see when we do random forest or Adaboost algorithm, right? Is that clear? So it is not redundant. We are just, you know, uh, enhancing the features, right? Okay, right. So, for example, again, as I was saying, you have some input, you have some multiple weak models, right? Model number one, two, three, four, and so on. And finally, you can do a voting. So you can do unweighted voting. So by unweighted voting, I mean that, okay, you have some example. So model one says the classifies the example. So, for example, if we go back to our heart disease problem, so the model one says, okay, this person has heart disease. Model two says, okay, this person has heart disease. Model three says this person has heart disease, whereas model four says this person do not have heart disease. So we can do a voting. We can say, okay, three models says heart disease. Then we can say, okay, this person has heart disease. So maximum vote wins. Final prediction would be this person has heart disease. Whereas for weighted voting, we can give certain weights to some models. So if we say that, okay, my this number one model is more accurate, is more robust, then we can give a higher weight to this model and lower weights to the remaining model. And then using those weights, we can predict the y value to the final prediction. Okay. Okay. All right. So coming to bagging and boosting. So these are two types of uh, ensemble learning methods that you frequently come across. And some examples of bagging could be this random forest algorithm. Some examples of boosting could be Adaboost, gradient boost, and AXG boost. And there are many other examples as well. In this lecture, we'll only do random forest and Adaboost. Okay, and I'll be taking an extra class on 14th, that is Saturday. So if you know, that will be mostly a question and answer session, and you know, we'll talk about the final examination. So I guess you guys must be, studying for that, and we can discuss some doubts that you have. And if I get time, I can explain some of the algorithms that we have left behind, that we didn't cover in detail in this lecture or in previous lectures. We can do that as well. Okay. So I might cover these things in that lecture as well. So again, so coming back to bagging and boosting, as I was saying that bagging and boosting are two methods of ensemble learning, and these are the examples of bagging: random forest. Example of boosting are Adaboost, gradient boost, and we'll see what are the difference between these two methods, right? And which is how methods to uh, make predictions. Okay. So first we will do bagging. So what is happening here? So if you have some original data set, so let's say that this is your training data, right? So you have this training data. Now there is a process called bootstrapping. Now this is a very simple process but very important. So what happens is that, so let's say you have n samples in your original data. Now you want to create a bootstrap data set. So how do you create a bootstrap data set? You randomly pick one sample and you replace it, right? So you pick one sample. So here, let's say this blue one. So they have picked this blue one first. They kept it back in the original data. Then again, next time, they also pick another sample from this data set. So let's say they take this brown one. So they have taken this brown one. Next time, they replace it and then again take one. So next time, then again, you see, they can take the blue one. So they can take the same sample again, right? So this is with replacement. Okay. So they replace it and then select one. And then similarly, they do it for repeatedly for n times, so that your bootstrap data set has such n samples. Okay. Right. Got it. Okay. So now this is your subset one. So what you do is you create this bootstrap data set, you make a subset. This is basically a subset of the original data, and you build a model on this bootstrap data set, right? So in the case of random forest, what you do is you make a decision tree, right? So we have explained in detail decision trees in one of the previous weeks. If you want to recall, you can go back to the previous lectures. Also, I've uploaded one lecture today where I explained how to make decision trees using Gini impurity, right? So if you want to revise those, you can go back. And Gini impurity is basically how these trees are made and how these cuts are made, which variables to choose, and all those. Okay. So basically, again, so as I was saying, using this bootstrap data, you make a model, you make a decision tree using this first subset. Okay, that is your model one. That is your weak model one. Now, what you do is you do the bootstrapping process. Okay, again, you take n samples. Actually, this happens simultaneously, right? So this bootstrapping these subsets, they make n subsets simultaneously, and then do the same thing for all these n subsets. You make a model on each of these subsets, and you make a decision tree. So the trees will be different in these different models, right? So as Prerna was asking earlier, that will this be redundant? So actually, this is actually the answer, that the same tree would not be in all the subsets, or even better, like these subsets don't have the same data. Even if the same tree is constructed, the data is different, right? So there will be some difference in between. And as I was saying in the previous slide, if you see the differences in this, you could have different algorithms, different hyperparameters, different representations, different training sets, right? So in this case, we have different training sets for these different models, right? Also, you could have different um, trees as well, right? So here you could have a two-leaf tree. Here you could have a three-leaf tree. In this picture, it is shown that they have the same trees, but in in random forest algorithm, you can have different trees. Okay. Now, uh, now what happens in random forest is that you do this bootstrapping. You build models on. You make decision trees on uh, all those bootstrap data sets, right? These are these are in your control. Like we'll do a see that how many subsets we want to make. These are in your control. You can change the number of subsets and you'll see that. So now you have built this n number of decision trees, right? So now you have n different trees. And here in this picture, although they have shown that the trees are same, but actually these trees could be different, right? So uh, now the question is, how should you predict uh, a new example using this random forest, using this set of entries, right? So when you have a new example, you want to predict, you pass that new example through each of these entries, right? And you record the output given by each of these trees. So, for example, model one, the decision tree one gives uh, says that yes, let's say heart disease, and decision tree two says okay, no heart disease. So, decision tree three says again like yes, that means one value one, and decision tree four says value zero, and so on. Now, what you do is do a voting of all these n number of trees. So, as I said earlier, that you could do either weighted voting or unweighted voting. So, unweighted voting would be just the majority of the votes, and weighted voting would be you give some specific weights to different number of different trees. So, based on the voting, you get the output, and whichever wins the majority vote, that is the prediction of your new sample. Okay. So that is all about bagging, right? Now, we would see what is boosting and what are the differences of boosting with bagging. So, as I mentioned earlier, that Adaboost, Gradient Boost, and XGBoost are examples of boosting, but there are some differences between these three models also. So, we'll explain Adaboost in this lecture, uh, and you can see what are the differences between Gradient Boost and XGBoost. So, but primarily we want to know what is the difference between bagging and boosting. So, in bagging, we saw we take the original data, we bootstrap the data, and then build n models on the bootstrap data, and finally we do the voting to see the prediction. In boosting, what we do is we take the original data, then we build a model on the whole data. So that is the first difference between bagging and boosting. So there is no bootstrapping involved in boosting. Build the model on the. So in this example, if you see, so these are the correctly classified samples by model 1, and there's the misclassified samples by model 1. So in brown and purple colors are the misclassified one. So now what we do is we make a new data set with a weighted data. And how we do the weighting is we put weights on the misclassified samples and we put lower weights on the classified samples. And why do we put higher weights? Because we want the next model to be built in such a way that it you know takes special care to those previously misclassified samples. So those misclassified samples should have higher weight in the next iteration, right? So that the model you know, works aggressively on those particular samples so that in the next iteration, those samples are not misclassified. So if you see here, so after the weighted data is built, you build a model on that, on the weighted data, and then you again do the same thing. You see which are correctly classified, which are misclassified. And if you see the previously misclassified samples, since they have a higher weight in the weighted data, now they are correctly classified, right? Whereas there could be some other misclassifications which were earlier correctly classified, right? Now you repeat the process. You do the same thing. Again, you put higher weights on the misclassified samples and lower weights on the classified samples, and you build another model and you repeat this n times until you get a n models, right? So again, you have this n trees, but in this case, the first difference was obviously bootstrapping, and the second difference is that this weighting of the misclassified samples on which you build the next model, right? So these are the two differences between bagging and boosting, right? Okay, now we will see one of the examples of boosting, that is Adaboost, right? So Adaboost. So this is a boosting algorithm that we discussed earlier, but here I will explain this particular Adaboost algorithm with one example. So let's say this is the data that you have, right? So this is the data of uh, 8 persons, right? And you have the data of their chest pain, blocked arteries, patient weight, and the target variable is heart disease. So, for example, the first person has chest pain, yes, blocked arteries, yes, and weight is 205. I hope it's in pounds. And this person has a heart disease, yes. Okay. So you have 8 such patients, right? And all their data are given here. Now we want to build an Adaboost algorithm on this data set, right? So initially, when you build the first model, so before you build the first model, you give equal weights to all the data set. So as I was mentioning earlier, you refine your weights based on misclassification, correctly classification. So initially, for the first run, you give equal weights to all the samples, right? So since there are 8 samples, the weight for each of the samples will be 1 by 8, right? Now what you do is that, uh, okay, so there is one particular thing which is very specific to this data boost algorithm only. So gradient boost and XGBoost will have uh, different things, but data boost. Uh, so the specific thing about data boost is that all the trees that it makes has only one node, right? So what do I mean by a tree with one node? For example, if you see the trees on the right side, so for example, this tree has chest pain, blocked arteries, only one node, right? So there are no further branches out of the second nodes, right? So these trees which have only one nodes are called stump. Okay, this is just a terminology. So Adaboost uses stumps only. Okay, gradient boost and XGBoost might use higher depth trees as well. Okay, but Adaboost, all the trees in the Adaboost are only stumps. So that is one difference. Now, what you do is that you build the first model on this. You build basically the first stump using this data. So what you could do is you could choose the node as chest pain, or you could choose the node as blocked arteries, or you could choose the node as patient weight, right? So if you choose the node as chest pain, so if chest pain is yes, then you say okay heart disease. If chest pain is no, then you say heart disease, no heart disease. And similarly for blocked arteries, yes, you say heart disease. If you blocked arteries no, you have no heart disease, and you similarly see how many samples you are correctly classifying and incorrectly classifying in each of those nodes. Similarly for weight greater than 176, you have heart disease, and weight less than 176, you have no heart disease, right? So again, to see how these cuts are made, why we choose this number 176, you can look at the previous lectures or the lecture I uploaded just today. Based on Gini impurity, you choose this particular cut and you do this particular branch Okay. So, okay, so you could build only these three possible stumps out of this data set, right? Now you have to see which stump is, uh, is better, which stump is, best among the three. So, because you could choose only one stump, right, for the first model at least, right? So you have to see which stump is performing better. So basically, which stump has uh, less misclassifications. So if you see this stump has two incorrect in this node and one incorrect in this node, so three incorrect misclassifications, and block artery similarly have four misclassifications, whereas this stump with weight as a node has only one incorrect misclassification, right? So this is the best term that you can intuitively see for the weight part. But we want to quantitatively see which is the best term out of this. So what is the quantitative measure of which is the best term out of this? So which is the first model that you want to choose uh, as your stump? So the way to look at it is to calculate the total error. So what is the total error? So if you see, so this is the sample. So there is one sample which is incorrectly misclassified. So which is the sample among this that is incorrectly misclassified? So it says that weight is greater than 176, which is false. So weight is basically less than 176, but still uh, it has heart disease. So it is saying no, but it has actually heart disease. So this is the sample, right? So right. So this is the sample that is incorrectly misclassified. So weight is less than 176, weight is 167, but still it has heart disease. But it is saying no heart disease. Okay. So the total error would be, the sample weight corresponding to this sample, right? 1 by 8. So if there are more misclassifications, so you just add the sample weights corresponding to those samples which are misclassified, right? But in this case, we have only one misclassification and the total error would be 1 by 8. Now you have to calculate the amount of say from the total error, right? So amount of say physically, it means that what is the proportion of the say of that particular stump. So how good is that stump? It is a measure of how better is that stump. The better is the stump is, the better it is in classifying the uh, data, uh, the higher the amount of say it will be. So this is a simple formula that you have to calculate the amount of say from the total error, right? That is half log of 1 minus total error divided by total error. So we saw that for this term, the total error is 1 by 8. Similarly, it's an exercise for you to calculate what is the total error for these two stumps. And from there, you can calculate the amount of say, right? So let's calculate what is the amount of say for this term from the total error, right? So you just put the value of the total error in this formula. The value is the value of total error is 1 by 8, and you just calculate it using a calculator. Okay, so that I will do, and let's see what the value we get. Okay, so you just put the 1 by 8 in this total error, and you um, calculate this thing. Okay, this formula. So it comes out to be, I just calculated using calculator, it comes out to be 0.97, right? So that means your amount of say here is 97%. So this tree, so amount of say is just the measure of how good this tree is, right? So we will see how you know, uh, uh, make the change the weights. You increase the weight of the misclassified sample and decrease the weights of the classified sample using this amount of say. But the amount of say here is 97. So that means this is a very strong tree. So this tree has a very high amount of say. So a stronger tree would have a higher amount of say. A weaker tree, which has many misclassifications, will have a lower amount of say. Right? That is just intuitive, right? So this, if you calculate the amount of say for the chest pain, blocked arteries, you will have a lower amount of say, right? So basically, you choose the out of these three trees, you choose the tree which has the highest amount of say, right? So it is an exercise to you that to calculate the amount of say for the chest pain and the blocked arteries tree, and you can uh, uh, find the amount of say, and you select the tree which has the highest amount of say. So in this case, this tree has the highest amount of say. So the amount of say curve looks something like this. Okay. So if your total error is very high, your amount of say would be negative, right? If your total error is somewhere in between like zero point 0.5, right? So zero point 0.5 is basically it's kind of random. You don't know, whether it's good or bad. Then your amount of say is basically zero. If your total error is very low, you can see that amount of say will be very high, right? So this is intuition about this. Okay. Now, okay. Now in the next iteration, so you have built model one. Now you know these are samples which have been misclassified. These are samples which have been correctly classified, right? Now you have to change your weight of the samples, right? So for example, as I was saying that this is the sample which is misclassified, right? So now you have to increase the weight of this sample. How do you increase the weight of this sample? Is the new sample weight is become old sample weight times e to the power of amount of say, right? So as I was saying, the amount of say is 0.97, and your new sample weight would be old sample weight, that is 1 by 8 times e to the power of 0.97, right? So that will become here, if you see, that will become 0.33. So if you see, the new weight has been increased for this sample from 1 by 8 to 0.33. 1 by 8 is basically 0.125. So 0.125 to 0.33. Sample weight has increased. And now for the remaining of the samples, you have to reduce the weight, right? So the new sample weight for the remaining of the samples will be the previous sample weight times e to the power of minus amount of say. So the old sample weight is 1 by 8 times e to the power of minus 0.97, right, which we calculated earlier. So the new weight will become, for the remaining of the samples which are correctly classified, they will decrease. They will become 0.05, right? Is that clear? Okay. All right. So there is one just last step, is that you normalize uh, this sample weights again, right? So by normalization, I just mean that uh, that the sum of all this weight should become one. So you basically you take this divided by sum of all this. This will become the new sample weight. Just the normalization that we have done earlier as well. The scaling we had did it multiple times actually. So okay, so this is the new normalized weight. So 0.49, right? Okay. So now using this normalized weight, so this will become our new sample weight. Okay. And then again we repeat the process. Okay. We repeat the process. So now this time this sample which will have a higher weight, and we'll build the next tree using a higher weight on this sample and lower weight on the remaining of the samples. And the new tree will be built. Right? Okay. So yeah, is that clear? So we'll go on, we'll continue this process until we reach the desired number of trees that we want, right? And the final tree would be the uh, so we'll make like multiple trees, right? All these trees will be there, and next step we'll see how to make predictions using, let's say we repeat this process 10 times, we'll have 10 different trees. And now how will we predict a new example that we have, right? We'll see that. So yeah, predictions using Adaboost. So let's say you have like you made 10 trees like that, by changing the weights, refining the weights and making a new tree, and then again refining and making new tree, and so on, right? And these are, and then you have a new example. So what you do is pass this new example to each of the trees, and let's say these are the trees that says that okay, this person has heart disease, and these are the trees that says this person doesn't have heart disease. Now what you do is calculate the amount of say for each of these trees, and you add up for the trees which says no heart disease, and you add up the amount of say for trees which says that it has heart disease. Now you compare which has higher amount of say. So if you see, the total amount of say for yes heart disease is 2.7, and the total amount of say for no heart disease is 1.23. So that means uh, the new example that you passed, it has heart disease, right? So that's how Adaboost make predictions, right? So that's it about Adaboost. Is there any question? Okay, just one point regarding the thing that I said here. So, okay, so you have now normalized the weight. Now, when you uh, like after this step, so this will become your new weight. So, how will you ensure that this sample has a higher weight, right? So, basically, what you will do, you will uh, repeat this sample in your next data set, in your next subset. When you will make the next model, you will repeat this data set, and the repetition will be in proportion to this weight. So we'll repeat this sample more number of times than the rest of the sample, right? So you'll repeat this sample. So if you repeat this sample 7 times, you have to repeat this sample 49 times, right? And so on. So proportional to the weight, you have to repeat this sample, and then you make your next model on the new data set that you created, right? So that's how you give a higher weight uh, to that particular sample, right? So if you don't have any questions, we can move on to the hands-on exercise. So we'll just here we will show how to build a random forest model, and then we'll show how to build a Adaboost model on a data set, and we'll see how the which model performs better and what are the accuracies and uh, whatnot. Okay. Okay. So okay, let me zoom in. Okay. So here again, I'm just calling the libraries. Here I am reading my data set. Okay. So this is the data set that I have. All right. So what this data set is, let me just explain in a minute. So okay, so these are the different, you know, features that you have: age of a person, work class of a person. Work class means whether he's a state government employee, self-employed, private employee, and so on. Education, marital status, occupation, relationship status, sex, capital gain, capital loss, hours per week. This probably hours per week the person is working, native country, and so on. So, based on all these features, you have to determine the income of that person. So, this is your target variable. Target variable is income. So, income is less than 50K or greater than 50K. Okay. So, these are the columns that you have, right? uh, and these are the description of the columns, and finally you can check the statistics of this all these columns, like what is the mean age of the data set. Mean age is 38, standard deviation, min max, and so on. What is the education, and capital gain, capital loss, hours per week, and so on. Like you can check the statistics. These are part of the data pre-processing steps. Okay. Okay, let me zoom in again. Okay. Okay, so these are the pre-processing steps, and now we are checking what are the categorical variables, right? So these are the categorical variables that you have, right? So for example, work class. So number of private employees. So this is the number of private employees. This is the number of self-employment. This is the number of local government. So if you see, there are like some entries with question mark in them, right? So these are uh, basically missing values. We don't know what is the work class of these people. So for 1836 samples, we don't know what is the work class. So we'll do how to missing impute these values. So we have done missing imputation in previous lectures. We'll again see how to do this. Okay. So yeah. So similarly, you can see the statistics for other uh, variables. For example, native country. These are the number of people from United States, number of people from Mexico, and India has 100 people, and so on in that data set. Okay. So for all those variables, you can see, and now you want to see what is the frequency distribution with respect to different. So yeah, okay. Uh, Let me do one thing. Let me. Okay. Okay. So these are the frequency distribution of the income variable. So 24.1% people has greater than 50k income, whereas 76% has less than 50k income. Also, you can draw this bar chart and see all this. Okay, bar chart, pie chart. So this is just to see that okay, you have decent representation, decent number of people from both income categories. Right? So that's what you want to see, so that your model is not biased. So this is uh, how many males have higher than uh, 50k income. So red one is the number of males having higher than 50k. Blue one is the number of females having higher than 50k. And here you have, sorry, this is the higher than 50k part. This is the lesser than 50k. So you just check correlation of these variables with income, right? So you can see that okay, from the previous graph you can see that higher number of males have higher than 50k and higher number of males also have lesser than 50k income, right? And so on. So this is just a comparison. This with another variable, race, with respect to race, right? So if it's white, black, Asian, and so on. So what is the income for uh, what are the number of people who have less than 50k income in case of white, in case of black, and so on, right? So all these variables you can see. Okay. So for example, private companies have uh, you know have higher income, right? So and so on. These are just the you know pre-processing steps, right? So here is something which I said earlier, that we will do missing imputation. So if you see that there are some values which had question mark, right, for native country. So what we'll do is we'll replace them with NaN. NaN is basically means missing, right? And for similarly for occupation, we had some values which has question mark. For work class, we have question mark values. We are just replacing them with NaN, right? Now we want to check the correlation matrix. Again, we have done this multiple times in previous lectures. So this is basically just saying what is the correlation between age and let's say capital gain. So this is the correlation, right? And similarly for all other variables, right? So you just want to see that these variables. So if any two variables has high correlation, that means that one of the variable is redundant. But in this graph, you don't see very high correlation between any two variables. So all those variables are independent of each other, more or less, right? So you can say that, right? So that's what you want, and then you want to go ahead and build your model, right? So you split it into test and training set, right? And you check whether how many training examples that you have. These are the number of training examples. These are the number of testing examples that you have, right? and these are the categorical variables that you have. So now one thing you have to do is that why you need to check what are the categorical variables, because when you are giving input in your model, you have to you have to basically, encode them into dummy variables, right? And these are the number of numerical variables you have. And again, you have to check what are the null values, what are the missing values in each of these classes. So if you see work class has 5% missing values, so if you remember, we just replace the question mark with null values with NaN. So these are the 5% of those uh, values in the work class, right? And so on, right? So again, this is the missing imputation part for all the uh, you know uh, work class variables and so on. We're just missing imputing the null values uh, and with the mode. So if you see, for example, the work class variable, right? So whatever the mode value of this work class variable, you just place that in the place of the missing uh, samples, right? And again, you just take the categorical variables, you just look at what are the categorical variables that you have, and you just encode them. So what is encoding? So encoding is basically, so let's say in work class, so you have this private sector, public sector, or state government, and so on, right? So you just what you do is that if, let's say, public sector is if a person is in public sector, so for that person, work class 1 would be 1 and remaining would be 0, right? So if you see here, remaining as 0, work class 1 is 1. Similarly, for, let's say, state government sector, work class 2 would be 1 and remaining would be 0, right? And so on. You just encode them in such a way, right? And finally, you look at the uh, test samples. You do it for the test samples as well, right? And you scale them. So this is something, as I was saying, you have to normalize the data, right? And then you separate your training and testing data set. And finally, you build the. So here is where you are building the uh, random forest classifier, right? So here your parameters are n estimators and random state. So n estimators is basically the number of trees that you want to have. So let's say you have 10 trees. So if you remember the random forest, we can build n number of trees, right? So we just build 10 trees, right? So and then we fit our model by training data X train and Y train, and we predict our model and we check the accuracy score, right? So with 10 trees, our accuracy score is 84.46, right? Now what we want to do is, let's try out an experiment. Like, let's increase the number of trees. So what will happen if we, make 100 trees, right? So we are trying with 100 trees now, right? So again, we fit the data, we build the classifier here, we fit the data here, we predict it, and we again print the accuracy. So if you see that, okay, now 100 trees has increased our accuracy to 85.21. So earlier we had 84%, now we have 85%. Okay. So you can try it out with more and more number of trees, right? Or you can try out with lesser number of trees, and you can see like how random forest behaves, right? So these are some of the things that you can do. Okay. So okay, so if you try with very high number of trees, then that is also not good. It may lead to the accuracy might not improve by a significant amount as well. So uh, and also very low number of trees is also not good. You don't have uh, you'll have end up with very high bias actually. Okay. Okay. So now, what we want to do is, let's say you build this 100 trees, and you want to check, like, okay, which is the out of these 100 trees, uh, which is the tree that is giving me the most, important features, most important predictions, right? So how will you do that? So let's say you have like 10 features, right? So out of those 10 features, you want to know which feature is uh, giving me best result for predicting my income, right? In other words, by looking at which feature uh, we can best predict the income of that person, right? So how will you do that? How will you check which is the best feature? So you will have to look at all those 100 trees and you have to see out of those 100 trees which feature is used in maximum number of nodes in those 100 trees. So which feature is used to cut the tree, which feature is used to make branches in the tree, and that is the feature which has been used for maximum number of times in all those 100 trees. That is the feature which is giving you most significant uh, inputs about predicting the target variable, in this case income. So in this case, if you see this final weight, this is the variable which is giving us uh, which is appearing in maximum number of nodes in those 100 trees. So this is the most important variable. So you can like arrange these all these variables, all these features in their uh, decreasing order of importance. So final weight has most importance, age has second most, capital gain has third most, and so on. And this feature, if you see native country 41, this has lowest importance, right? So random forest not only builds you or gives you a model, it also gives you the importance of the features, right? And similarly, you can build another model by dropping the least important feature. So in this case, native country is the least important feature. So what you do is drop this feature and then you build again a model, right? With 100 trees. And this time, if you see, your accuracy has, I guess, improved a little bit. So earlier it was 85.21, now it's 85.44, right? So this is a, this is something you will encounter in multiple times if you in practical life. So if you remove some unimportant features from your data set, you can get better predictions using the same algorithm, same method. Okay, right. So you can try out by removing other features as well from the bottom. Like let's say work class 8, you can remove this feature and again test your model and get the accuracy and so on. You can experiment with it, right? So now coming to confusion matrix. So if you see, we do this. We have done this a lot of times in classification problems. So these are the true positives, these are true negatives, and these are actually negative but tagged as positives. So these are false positives, and these are false negatives, right? So from there, you can calculate the precision, recall, and F1 score, and so on. And you can check which model has the better precision, recall, and so on. Right? Okay. So again, this is where you are calculating precision, recall, F1 score, and so on. Right. Now, what we do is we want to train the same model using Adaboost. Right. Sorry, same data using Adaboost. So here we fit our Adaboost model, right? Uh, so here we make our Adaboost model, and here we fit it with our training set, right? And here we predict it using X test and find the accuracy. So if you see, the accuracy has increased. Earlier it was 85.44 using random forest, but using Adaboost, the accuracy is 85.87, right? Okay, you can also experiment with it. You can also here like uh, you know check out with different number of trees for data boost and so on, and finally you can calculate the confusion matrix. Okay, so here if you see, if you compare the confusion matrix forest, you can see that okay, 6931 is the false positives, so the false sorry, true positives, so the true positives has increased. Okay, but these are the false positives, 476 here, and here it was 540. So false positives has increased, so has decreased. Basically false positives has improved, right, in the Adaboost model. But if you look at the false negatives, 882, here the false negatives has increased, 904. So depending on your problem statement, whether you want to increase whether you want to decrease false positives or false negatives, you can choose this model or that model, and you can decide which model gives you the best results, right? Okay, so these are the two algorithms that we saw in action, random forest and Adaboost. And let me know if you have any questions. These are some of the questions. Like every week, we'll end with some questions for you that you can try out yourself. So, uh, yeah. So here we saw a random forest classification model, right? Whether the income is higher than 50K or less than 50K. You try to find out, try to implement a random forest regression model as well in Python. Right? You try to see how that, uh, what is the theory behind it, and try to implement it in Python. Also, as I said, there are like multiple boosting uh, algorithms that you have, like gradient boost and you know XGBoost and so on. So try to read up on the differences between Adaboost and gradient boost, and try to implement a gradient boosting model in Python, and similarly do it for XGBoost as well. Try to see what XGBoost is and try to implement an XGBoost model in Python. Right. So these are some of the exercises that you can do. Also, you can play with the uh, notebook that I just we just saw on random forest and on Adaboost. You can try to play with the parameters, number of trees, and so on. Right. So that is it. Yeah. Let me know if you have any questions.